So it's a pleasure to welcome Marcos Origlia from the Universidad Nacional de Córdoba, speaking on conformal killing Yano 2 forms on Lie groups.
Okay, thanks, Caroline, and thanks the organizer for this opportunity to give a talk in your seminar. It's a pleasure to me. So as you said, I will talk about conformal killing form, mainly on Lie groups. So in the first part of the talk, I will recall some basic stuff, definition, and so on, this topic, and then I'll focus on this work I did with Cecilia Herrera, also from Universidad Nacional de Córdoba. Let's start. So let me recall what the differential and conformal killing P form is. So Mg is a Riemannian manifold. Then omega will denote a P form, which is called conformal killing or conformal killing Yano, will denote it by CKY. So if satisfied this equation. So I don't know if everyone knows about this, but this is a kind of combination between d omega and the codifferential of omega up to some factor. So here x star denote the dual form of the vector x. This star is the codifferential operator. Nabla is the Levi-Civita connection associated with the metric. And there are particular situations of this equation. So for instance, if in addition the P form is co-closed, so this star omega equal to 0, like here. So the omega is called killing Yano P form. And on the other hand, if omega is closed, then it's called star killing P form. So this is a kind of a generalization of the killing, of the normal killing Yano P forms. And also there are generalization of the well-known killing vector field. So in the case of one form, killing one form, omega is a killing one form if and only if its dual is a killing vector. So this was so this appeared firstly in Yano paper in the 50s, and then we have the generalization of conformal killing vector. So this generalization is a conformal killing one form. So this was made by Kashiwada in the 60s. So you can see the conformal killing equation like a generalization of the usual killing forms, P form, or actually as a generalization of the killing vector field. So let me just mention some general properties about this equation. So for instance, if omega is a conformal killing P form, then the star of omega is again a conformal killing, but now n minus P form. So n here denote the dimension of the manifold. So actually, this the Hodge star operator interchange close and co-close conformal killing form. So it's closed by this operator, the Hodge star operator. Also, there's another property, the second one, which is the conformal invariance. So if omega is conformal killing, a conformal killing P form, then if we change a little bit the metric by a conformal factor, we can obtain again another conformal killing P form just by doing a similar change in the P form. Of course, will be a conformal killing P form with the new metric, right? Another nice property is when you study the space of solution of this, the vector space of solution of this this equation. So conformal killing, sorry, P form. So this space of solution has a finite dimension, and Semmelmann proved that the dimension of this space is bounded above by this number. So again, n is the dimension of the manifold, and while we are talking about P form, that's why the P plus 1 here. And we got full dimension in, for example, in the case of the standard sphere, we have the full dimension of this space, and actually, when you get the full dimension of this space, the manifold has to be conformally flat. And the last property is that conformal Killing P form on compact Riemannian products are sum of parallel form, pullback of Killing form on the factor, and possibly their Hodge dual. So this was proved by Moro, Yano, and Semmelman in this work in 2008. So these are just some properties of in general in manifold. So here let me introduce the main two examples of this Killing and conformal Killing forms. So about Killing form, we have nearly Keller manifold. So on any nearly Keller manifold, M, J, G, and J is the almost complete structure. So here the fundamental two form, omega, determined by the almost Hermitian structure, is a conformal Killing two form. It's a Killing two form, right? And actually, it's the only case when this happens. So in general, this is a fact. So if M, now dimension to N, G and J is an almost Hermitian manifold, then the Keller form is a conformal Killing two form, if and only if the manifold is nearly Keller. So notice that here we have conformal Killing. So at the end will be just a Keller two form, but only happen in nearly Keller manifolds. So this was about Killing forms, actually Killing two forms. So what about conformal Killing? And we are interested in the case when this conformal Killing form is actually strict, which means that it's not a Killing form. So conformal, not Killing. That's will be our case. So the main example here are given by Sasakian manifolds. So let me recall briefly the definition. So we have M, dimension 2n plus 1. So the metric, some endomorphism phi, alpha is a one form, and this is special vector, the Riemann vector. So this is a contact manifold with this integrability property. So with the standard definitions, it's not clear at all that we have a conformal Killing two form, but there is an equivalent characterization or definition of Sasakian structure on a manifold, and it's given by this one. So Mg is a Sasakian if there exists an unit length Killing vector field, that will be the Riemann vector field, such that satisfy this equation. So nabla x, the C star is equal to this guy. So this is exactly, if you remember, this is exactly the equation. Let me go back. So this is exactly the equation of conformal Killing, just with the second part, with the second term. Of course, this is close in our case, but we have just the second part with p equal to 2, right? So here. So this is clearly an example, sorry, of a conformal Killing two form. So given by the differential of the dual of the Riemann vector in a Sasakian structure. And actually, in some case, this is more or less the only case when this happened. I mean, so here we have a Killing vector field, the Riemann vector, and the differential of its dual is a conformal Killing two form. So if we add the condition to be Einstein, so this only happens when the structure is Sasakian. So this is the result. So all of these, those three results are in this work of Uwe Sebelman, so which is a nice work about conformal Killing form. So if M, now dimension is n, is an Einstein manifold, so we have to normalize the scalar curvature. And if we have an unit length Killing vector field such that the differential of its dual is conformal Killing two form, So then this vector has to define a Sasakian structure. So it's only happening in Sasakian manifolds if we add the condition of being Einstein. Some other property of Sasakian is if M is a Sasakian manifold with a conformal Killing vector field, the rib, then we have examples of 2k plus 1 conformal Killing form. We have just to do the dual of this vector, which the differential of it to the power k. And we have examples of 2k plus 1 conformal Killing form in Sasakian manifold for any k. And one extra property of our main example is that any conformal Killing form of even degree is a sum of a Killing form and star Killing form. So in the main example, you see conformal Killing form are just very special. They are either Killing, star Killing, or combination of both. We will see at the end that in our example, we have a conformal Killing which are not of this type. Well, nice. This was general stuff about conformal Killing. We will focus on two forms, conformal Killing two form. Yes.
Are there topological abstractions for existence on a compact manifold for, say, two forms?
Sorry, I couldn't hear you at the end. Topological restriction for conformal Killing forms, you said?
For the existence of conformal Killing two forms.
Yeah, I think there are some on compact. Let me think. Wait, yeah, probably there are a lot because they are very weird examples. I mean, they're only basically one example, which is given by the Sasakian. So you can think about this conformal Killing two form as generalization of Sasakian structure, actually. But yeah,
okay.
Is Cecilia in the audience? Probably not, right? No.
And another question.
Yeah.
Three forms.
Sorry.
This conformal Killing three forms. Do they appear in some geometry, in some problem?
Well, at the end, in dimension 5, there will, I mean, basically three form is exactly the same that two form because you take the Hodge operator. But in general, you mean? I think there are some conditions in geometry. For example, there are some conditions related with parallel. So if you have a connection with parallel torsion, so this three form is related with this three form. So actually, I don't know if they are examples. Yeah, probably they are example of three forms. So when you have a torsion which is parallel, probably they are example of conformal Killing three. Yeah, I don't know. I'm not sure, but they're a relation with parallel torsion.
Okay, thanks.
But yeah, our result will be just we study two forms, and as a consequence, we have some result related with three forms. And sometimes this happens because of the dimension of our manifold. Well, so here we have an easier characterization of this equation. So this characterization, I think, was made by Semmelmann. So it also works in general, not only for two conformal Killing forms. It's held in general for P forms, but I just mentioned the situation for two forms. So omega is a conformal Killing two form if and only if there exists a related one form denoted by theta on our manifold, such that this equation in red holds, right? So the left side is similar to the left side of the original equation, and then you can play around with this and show that this is the other side. So for examples, when we have to do our computation, this characterization is much easier than the original formula. And in this situation, this one form is given by this. So it's determined by omega and the codifferential operator. Again, here n is the dimension of the manifold. So we work with this equation. Okay, that was general stuff of conformal killing and killing P form on manifold. Now we will focus on the invariant case on Lie groups, which is the main source of examples. The known examples mainly happen in Lie groups and with left invariant structure. So G will denote the Lie group. The Gothic G will be its Lie algebra. As usual, we have a left invariant metric, and we have this relation between left invariant metric and inner product in our Lie algebra. Our two form will be left invariant if satisfied this condition. LA is the left multiplication by A. And here, if omega is the left invariant conformal Killing true form, so then remember the definition of theta, which is related with omega. So theta is also left invariant. So our equation can be defined at the Lie algebra level. So we will work on G with our inner product, and we will call a conformal Killing true form if satisfied the equation at the Lie algebra. And we also sometimes it's easier to work with the tensor associated to this two form. So any conformal Killing two form determine an skew symmetric tensor with respect to the fixed inner product, which is an endomorphism T satisfying this equation, right? So the same equation we had for omega, so we have the same equation for T. This equation in blue is our main tool to get examples, and at the end our classification in dimension 5. So here theta is the integral of the Lie algebra, and we will call just the conformal Killing tensor to this T. So talk about conformal Killing tensor or conformal Killing two form is the same. Now some known result in the invariant case. So for Lie groups. So what happened in dimension 3? Well, it's done. So conformal Killing two form. So I'm talking about two forms here. On three-dimensional Lie group were classified by Andrada, Barberis, and Dotti in one of these paper. Then there is also a result in this work of Andrada and Dotti. It says that any conformal Killing two form on a 2n dimensional Lie algebra, so the conformal Killing two form is actually Killing. So if you are interested in a strict conformal Killing two form, which are not Killing, so your dimension has to be all, right? And moreover, in particular in dimension 4, they are not only Killing, but they are parallel. So any conformal Killing two form in dimension 4 at the end is parallel. This was proved by Andrada and Dotti in the invariant case, but it's also a more general result in this other work of Andrada, Barberi, and Yano, that if a conformal Killing two form with constant length, so has to be parallel. That's the result. In particular, in the left invariant setting, in dimension 4 oral parallel. So next, the next natural step is just to consider 5-dimensional metric Lie algebra and study this strict conformal Killing two forms. And in this case, in dimension 5, what is known, well, all the examples we know are given by Sasakian structures. So Sasakian manifold in dimension 5. This was done by Andrada, Fino, and Bezzoni. So in their work, they classify some class of Sasakian. So the class that the dimension of the center is equal to 1, so they come from a Keller extension of 4-dimensional Lie algebra. So we'll use this idea in our setting to classify some class of conformal killing two forms. So this is the first part of our paper with Cecilia. So our motivation was just try to find examples of this conformal killing two form, which are not come from Sasakian structure, right? Well, the first part will be some conformal killing which are related with Sasakian, but at the end we have more examples which are not Sasakian. So let me just mention two results in this work of Andrade and Dotti. So if T is a conformal killing tensor on a metric Lie algebra, so this special vector, so the dual of theta, satisfy the condition that T vanish on it. So T of this vector is 0. And then we have this other result, which I already mentioned something, that says that the dimension of the manifold is odd. So it's this conformal killing tensor. If this one form is not 0, then the dimension of G is odd. And we have another condition, which is which says that the two form has full rank, right? So if we restrict T to the orthogonal complement of this special vector, so it's a linear isomorphism. So this is an instruction of the dimension of the Lie algebra. So in our case, we are interested in example with theta different from 0. So that's why phi is the first interesting case. And one more remark. So anytime you have a conformal killing tensor T, so again determined by this theta and this unique vector. So if you multiply this tensor by any constant, you have another conformal killing. You need just to also multiply by this factor the special vector, right? So anytime you have one example, actually you have one-dimensional a line of example, right? So there is not loss of generality if we assume that the length of this special vector is 1. Okay. So this is the first part of our work. We split the situation in two cases. So mainly the first one is what's happened when this special vector is in the center of the Lie algebra, and then we will consider the opposite situation. So here we have metric Lie algebras with conformal killing two form with this extra condition. So this special guy is in the center. So here we will combine two results. So this is the result of Andrade and Dotti, which says that a strict conformal killing tensor are related, with killing tensor in a smaller Lie algebra. So if H is an invertible killing tensor, then you can make this central extension of the Lie algebra with mu. So these are the mu Lie brackets. And if you take just the restriction T, the new tensor is S in H, and then you define it, extend it by 0 in the new direction. So then this T is a strict conformal killing tensor. So conformal killing, but not killing. And this is always the case. So conversely, if you have a Lie algebra admitting one strict conformal killing tensor such that this special vector is in the center, then has to be an extension in this way of a smaller Lie algebra with an invertible killing, right? And moreover, the center is generated by this guy, so dimension 1 of the center. So in dimension 5, we need to pay attention to 4-dimensional metric Lie algebra with killing tensor, but as I said, they are parallel. And Cecilia in her work, she classified all four-dimensional metric Lie algebra with parallel skew-symmetric endomorphism. So if we combine her classification with this result of Adriana and Isabel, well, it's not hard to get the classification of conformal killing in dimension 5. And that's what we did in the first part. So basically, well, we have this result. So any 5-dimensional metric Lie algebra with this extra property that the special vector is in the center of the Lie algebra, then the dimension of the center is equal to 1, and G is isometrically isomorphic to one of the Lie algebras in this list. And one extra thing is the conformal killing tensor is uniquely determined by the metric Lie algebra. So it's up to scaling, there is only one. So this is a list of 4-dimensional Lie algebra with a central extension. So in most of the cases, Cecilia classified the parallel skew-symmetric tensor, and there is a parameter in the metric. Maybe we just can pay attention to the last one, which is the central extension to the abelian Lie algebra by this mu. And here there is only one metric. But what's happened with this list is we have a lot of Lie algebras with some parameter, but all of these as a Lie algebra are isomorphic to only one, I mean, in each line, right? So what we did next is just to do a change of basis and put everything in one fixed basis with no parameter, and we can translate all the parameters to the metric, just to see what are these Lie algebras, and that's what we have in this ugly table. Maybe we can just pay attention to the last one. So of course the central extension of the abelian 4-dimensional Lie algebra by this new direction is just H5, which is the 5-dimensional Heisenberg Lie algebra, right? And now the parameter A1, A2 are on the metric. So here the metric is diagonal and involve A1 and A2, right? So previously those parameters were in the Lie bracket, right? And in this case, the conformal killing 2 form is given by this omega in the second column, right? Last row. And the same happened with all the other extensions. So most of them, the metric is diagonal except for this one, and there are a lot of parameters in the metrics, right? So we get this classification. So there are these families with the metric and the conformal killing 2 form. But the important fact is there is only one. I mean, when you fix your metrics, so this metric determines uniquely your 2 form. So at least of this type, there is only one conformal killing 2 form.
So Marcos,
yeah.
Do they admit a killing also, all these Lie algebras?
Well, a priori it can be, but at the end we will see that it's not the case. So in our list there is mainly only one, which is this one.
But these are, you said, strict conformal.
Yeah, but at the end I will say something about the whole space of conformal killing, including the killing. Yeah.
The only ones.
So this one are strict, but at the end we will see that they are not killing in this case.
It's determined by the metric actually. The 2 forms.
Exactly. Yeah.
Okay.
But pay attention that we are in a particular situation when we said that this special vector is in the center, right? So maybe there are another kind of conformal killing with this special vector not in the center, right? So same Lie algebra, but maybe another metric, right?
Okay.
But in this case, with this family of 1 or 2 parameter metric, they are not killing. We will see at the end. Okay. So let me just do 2 remarks about this classification. So with this classification, we can. sort of recover the classification of the Sasakian I mentioned in this work of Andrada, Fino, Bezzoni. So as I said, they construct or they classify this Sasakian, which are a central extension of Keller four-dimensional Lie algebra. So as Cecilia classified all the skew-symmetric parallel endomorphism in dimension 4. So in particular, when they are complex structure, we have the Keller four-dimensional algebra. So this list includes the Sasakian structure. And to see that, for example, in the last one, I think is in all the cases you need to take the parameter A1, A2 equal to 1. So in that case, the original skew-symmetric parallel endomorphism is actually a complex structure, and then it's produced a Sasakian structure, right? So in our list, there are examples of Sasakian and non-Sasakian. That's the point. And the last remark of this part is about compact samples. So in the list I show you, there are only two unimodular Lie algebra, which is G3 and the Heisenberg one. And the associated simply connected Lie group in both cases admit lattices. So we already knew but the Heisenberg one, but in this work of Andrada, Fino, Bezzoni, they construct explicit lattices for the simply connected Lie group associated with G3. So in both cases, we have compact examples. Okay, so now the second part. So in the second part, we will consider the situation when the dimension of the center is not, or is greater than 1. So remember, if we require that this special guy is in the center, then it has to be a central extension, as I said, but also the dimension of the center is 1. So in general, in dimension 5, the center is bounded above by 3. So there are two more situations, dimension 3 or dimension 4. In dimension 3, we prove with Cecilia that there are not examples of strict conformal Killing tensors or strict conformal Killing 2 forms when the center has dimension 3. So the only possibility is dimension of the center equal to 2. And in this case, we have this this result which actually holds in general, not only in dimension 5, that if you have a strict conformal Killing tensor and theta is the associated one form, if the dimension of your center is equal or greater than 2, then the center is in the kernel of this one form. So in particular, our special guy is orthogonal to the center. So this is general, not only dimension 5, but with this result, we can get the composition. We will see the composition of the Lie algebra, which allow us to get some equation and classify at the end. So this is the idea. So we get very arbitrary situation. 5-dimensional metric Lie algebra. T is a strict conformal Killing tensor. That's important. It's strict. The special vector is unitary. Then we have an orthonormal basis. Set 1, set 2 are the guys in the center. And then we have two more elements. This is the general form of a conformal Killing 2 form. And we have the Lie bracket. Everything free till here. Then we have the condition to be conformal Killing. And we apply this equation, and we try to reduce and hopefully classify all the possibilities in dimension 5 with this condition on the center, right? Dimension on the center equal to 2. So the reduction is given in two parts. So the first part is this proposition. So it's such a Lie algebra with a strict conformal Killing tensor, well, and then it's isometrically isomorphic to only one of these. So the whole, so we had many parameters on the bracket, A1, A5, B1, B5, the same with C, and we reduced them to only to R and S, right? The metric is the same. So if the Lie algebra meets one of those strict conformal killing, then it has to be one of these GRS when the Lie bracket are given by this formula 3. So R is this combination of A1, A2, and A4 is just, I wrote A4 instead of this S square minus R square over S. But everything is determined by A1, A2, and A4. So the rest of the parameter are 0. And of course, C5, which is S. And we can assume that this S is positive. Otherwise, you do a change of X and Y, and you have the other case. And moreover, for one of these Lie algebra, the conformal killing two-form or tensor is given by this. So again, is completely determined by R and S, which it was not clear at the beginning, because remember we had so A, B, C, D, E, F. So it happened that we can have some freedom in the parameter of the tensor, but at the end, when you apply the equation, so the metric Lie algebra determines uniquely this two form of the tensor, right? So there is only one strict example. And the idea is the proof, well, it's just use the equation. So what we did is, remember we have this result about that this special vector was in the orthogonal complement of the center. So this allows us to write the orthogonal complement of Z like the center plus some orthogonal part. And then if we pay attention to two operator, which is of course T, and this add C, restricted to the orthogonal of this vector, then we can write these two operator as blocks, 2 by 2 matrices. And playing around with the equation, we have that the conformal killing condition implies some equation of this block. For example, the first one, AQ is equal to 2 times the identity, which means that Q is completely determined by A. So that's why you see that the Lie bracket determine at least this part of T. And again, with the other equation, you can see that your structure constant reduced to GRS, as in the statement, and T has only one option. It's completely determined by R and S. One observation is all these Lie algebra are unimodular, and they are paired with not isometrically isomorphic, right? But again, so we have two parameters, so two parameters in R and S in the Lie bracket, and one fixed metric. We prefer just to see the Lie algebra with the family of metrics. So we did exactly the same that in the previous case. So we just put everything in one fixed basis, just to see how many Lie algebras in dimension 5 we have, and this is the final result of the classification.
Marcos, do you use Ricci eigenvalues to prove that remark?
Ricci eigenvalues, no.
What do you use?
I mean, which to see that they are paired with not isometric isomorphic.
Yeah.
No, it's just we write what's happened in the case of R, G, R, S, and R tilde, S tilde are isomorphic. Let's see. Maybe yes, at some point we use that. Yeah, probably. But it was a direct computation. If there exists such an isomorphism, then the parameter has to be equal. So, I mean, the only possibility for such an isomorphism is just some rotation of the center and some rotation of X and Y, and probably change the sign of the real vector, right? There are not other possible isometries.
Anyway, it would be interesting to know if they are geometrically, I mean, with rich eigenvalues, right? If they really
probably yes, it's a shorter proof.
and also if there is a Ricci soliton there
for this family of metrics, the algebras.
Yeah.
Okay.
Only one. Because, sorry, but I mean, they are non-isomorphic. No, some of them are isomorphic.
No, as Lie algebra, you mean? Yeah, there are a lot of isomorphic. Actually, yeah, in the next slides, you will see that there are only 3 Lie algebras with a lot of metrics, of course. But yeah, this is the result. So there are, with this situation, admitting one strict conformal killing tensor, if the dimension of the center is greater than 1, then there are a lot of families, but as Lie algebra, there are only 3. L59, these are 2 times SU2 and R2 times SL2 R, right? And all the parameter RS now are in the metric. So in the first case, so this L59 is an nilpotent Lie algebra, 3-step nilpotent Lie algebra, dimension 5. And the metric, you see, depend only on one parameter. And in the other 2 cases, we have the other Lie algebra and this ugly metric in each case. So the metric are really similar. And moreover, again, as I said, the tensor or the conformal Killing 2 form is again uniquely determined by the metric, right? So there's a lot of possibility for metrics for those 3 Lie algebras to admit these tensors, but if you fix the metric, there is only one. Up to scaling, right? Remember that we always can change the length of the special vector and also t. So these are the 3 Lie algebras with the corresponding metrics, and this is the conformal Killing 2 form for each case. Well, the first one is not so bad, but the other 2 are quite involved. And the idea of the proof is very simple at this point. So there are only 3 situations when the parameter RS are equal. In that case, you get the nilpotent one. And depending if S is greater than R or the other way around, you have the other 2 possibilities. So in this case, we use SAGE to check that there are not more conformal Killing 2 form for those Lie algebra. Actually, we use SAGE a lot to check all the stuff. And again, we have a similar remark here about compact examples. So any lattice we have for the associated simply connected Lie group GRS, so it's determined a conformal Killing tensor in the quotient induced by T. Of course, we know that those manifolds do not admit any invariant Sasakian structure because the dimension of the center is greater than 1. But maybe probably they admit non-invariant. Well, for the nilpotent, for the nil manifold, this is not the case. So in the nil manifold, so G mod gamma is the nil manifold associated with the Lie algebra L59, they do not admit any Sasakian structure, invariant and non-invariant. Because I guess that nil manifold, if a nil manifold admits a Sasakian structure, the only possibility is the Heisenberg. And this is not the Heisenberg, so it's a 3-step nilpotent one. And in the other 2 cases, well, for the second one, R2 times SU2, so the compact manifold admits non-invariant Sasakian structure. And for the last one, we don't know. But at least in the nilpotent case, so this is an example of the compact manifold with this one of these strict conformal Killing 2 forms, and they do not admit any Sasakian. So they are really different from the known examples.
So Marco,
in
the second case, you are using some topological abstraction, S3 times T2.
To know that it admit non-invariant, you mean?
Yeah, you are
Yeah,
using
there
some topological abstraction.
are, but they admit.
Ah, they admit. So, oh,
Yeah,
okay,
yeah.
sorry. And for
Yeah.
nil manifolds, is topological the problem, or
I don't know what is, how is the proof. I don't know. I only know that, yeah, if an nil manifold admits, it has to be the Heisenberg. But yeah, I don't know what is the proof.
Okay, okay.
Okay. Well, so at the end, just something about this this space of the vector space of solution of the conformal Killing equation. So as I mentioned at the beginning, there is this vector space is bounded above the dimension, is bounded above by this number. So in case of two form, it's between 1 and 35. But as we will see, in our cases, the dimension is 1. So again, now I will say something about the first situation when this special vector is in the center, and this is the result. So if we have an Lie algebra with a strict conformal Killing to form, in other words, so the codifferential of these two form lies in the dual of the center. So it's the sign that says that this special vector is in the center. So in this situation, so there are not Killing to form, and the conformal Killing, of course, they are strict. They are actually star Killing, right? So they are not co-close, but they are close. And there is no more, right? So in particular, they are not non-zero parallel tensors. The idea of the proof was just case by case. So we took, remember,
sorry,
this is the, yeah.
You mean star Killing 3 forms? Or?
No, in this case, I'm talking about 2. So what we prove is conformal Killing 2 form,
yeah,
are strict, and actually they are star Killing, right? That's why star Killing 2 form are equal to Killing.
It does
So
not mean that the star of a Killing 3 form. No.
No, because it would be a Killing 2.
Okay, okay.
There is this duality between, yeah, star and not star, but remember the dimension.
Okay, okay.
And the proof was just case by case. We took each of the Lie algebra of the table I show you with this condition of the center, and we proved that, yeah, the only possible solution for a conformal Killing, strict, non-strict, is just the one I showed you in the table, and that one was closed. That why is and star Killing to form. That was the difference. What's more? So in particular, so G does not admit non-trivial Killing, as I mentioned, but also strict Killing, conformal Killing to form, such that the codifferential is not in the dual of the center. So if you assume that this vector is in the center, we have one strict example, and there are not more. That's the situation. Okay, and finally, well, what happened with the other case when the dimension of the center is greater than 1? So in this case, again, the dimension of the space of conformal Killing 2 form is 1, but it's different because, well, same as the other example, the Killing 2 form, they are not Killing, but here we do not have star Killing 2 form. So that's the difference with the previous case. So what we prove is our examples of a strict conformal killing two form are not close, but they are also not co-close. So it's not a combination of close and co-close that happening in the Sasakian case. And the proof is just a reduction to the three-dimensional algebra. So if you assume that there exists a strict conformal killing two form, so we prove that it's never closed. And then if you take, so the only thing we need to check is if there is some killing to form in this case. But if there is some killing, then this killing goes to the quotient of the Lie algebra by the center. And this quotient is just the Heisenberg, SU2 or SL2. But there is a classification of three-dimensional Lie algebra with killing to form, and they are just those two, E2 or the extension, trivial extension of the affine Lie algebra. So they are not killing to form. So the only conformal killing is the one we exhibit in the classification. And again, as I said, it's not killing and it's not star killing. So this is very, I mean, it's very different when this situation what happened in the Sasakian case, when everything is a combination of killing and star killing. Okay, and finally, well, some open problem or situation that they are not solved even in dimension 5. For example, conformal killing two form, but now with this special, with the dimension of the center is trivial, well, this case was not analyzed, and also we don't know what happened if the dimension of the center is equal to 1, but this special guy is not in the center, right? And also, yeah, it's not know what's happened with killing P forms, not just 2P in dimension 5. And another possibility we are working with Cecilia is what's happening in 3-step nilpotent Lie algebras with killing or conformal killing. So about 2-step, it was a study by Andrada and Dotti. So killing two form in 2-step nil manifold, and by Del Barco and Moro Yano, the case of conformal killing is 2-step. So the next case would be 3-step. That's some possible continuation. Yeah.
You have an example.
Yeah, our example in dimension 5 is 3-step. That's why we are interested in trying to generalize this example.
Is the first example in 3-step?
That, yeah, at least that I know is the first example. Okay. Yeah. But what is weird is this is very different from the Sasakian case. So because this manifold do not admit any Sasakian structure, and actually this example is not the combination of killing and star killing. It's very of mixed type. Well, I think that's all I want to mention. Thank you.
Thank you very much for a very nice talk. Are there any more questions? Well, if not, thank you again.
Okay, thank you.
And I want to mention, because the International Congress is coming up, we won't be meeting in 2 weeks, so we'll be resuming in, I guess, 4 weeks. So thank you.